This question is about some reactions of D-block elements and their ions. Table 21.1 shows standard electrode potentials which will be needed within this question. Part A. Complete the electron configuration of an Ni atom and an Ni2+ ion. The electronic configuration for a nickel atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. For a nickel 2+ ion, most of the electronic configuration from the nickel atom will stay the same. So we'll have 1s2, 2s2, 2p6, 3s2, 3p6, but here at the end we're going to change the electronic configuration to lose 2 electrons because we're forming a nickel 2+ ion. We're going to lose both 4s electrons because they are filled first and lost first. So to complete the electronic configuration we'll have 3d8. To get the 2 marks for this question, you get a mark for each electronic configuration that's correct. So a mark for the correct electronic configuration of a nickel atom and the correct electronic configuration of a nickel 2+ ion get you your 2 marks. Part B. A standard cell is set up in the laboratory with the cell reaction shown below. Part 1. Draw a labeled diagram to show how this cell could be set up to measure its standard cell potential. Include details of apparatus, solutions, and the standard conditions required. To begin, we need to draw 2 half cells. Half cells are measuring cylinders, so we need to draw 2 measuring cylinders with a solid electrode in each. These electrodes are connected by a voltmeter and they are surrounded by aqueous solutions filled with ions. These solutions are connected by a salt bridge. You need to label salt bridge, and what a salt bridge is filter paper soaked in ionic solution such as KNO3. So what the electrodes are and what the ionic solutions are, we need to determine. So nickel is a solid. That means it can be an electrode. So we can label an electrode as nickel. But the 2 iodine and iodide parts of this equation are both aqueous, so they cannot be an electrode. Therefore, we're going to use a platinum electrode, and in the ionic solution we will have I2 and I-. But in the nickel electrode solution we will have Ni2+. Next, the standard conditions. The standard conditions are all of the solutions need to be 1 mole per decimeter cubed in concentration, and the temperature needs to be 298 Kelvin, which is the standard condition for temperature. To get the 4 marks for this question, you get 1 mark for having a voltmeter and salt bridge, a mark for 2 correct half cells, so that's 2 marks for each correct half cell, and then you get your 4th and final mark for the standard conditions being correct. Part 2. Predict the standard cell potential of this cell. In this question, we're using the electrode potentials for the nickel and iodine. To work out the standard cell potential, you take the more positive electrode potential, which would be 0.54, and you minus the most negative, so minus 0.25. That would give us a standard cell potential of 0.79 volts, which we can write on our answer line. To get the mark for this question, you need to have the correct standard cell potential. Part C. Use the information in Table 21.1 to help you answer both parts of this question. Part 1. Write the overall equation for the oxidation of Fe2+ by acidified H2O2. Firstly, we need to identify the electrode potentials we're using. So here I've highlighted them. Next, we need to look at their electrode potential values. The most negative, in this case Fe2+, will go backwards, and the most positive will go forwards. So rewriting these equations, we would have Fe2+ goes to Fe3+ plus an electron, and then H2O2 plus 2H plus 2 electrons goes to 2H2O. Next, we need to scale the equations. So we need to match the electrons, which means we need to multiply the ion equation by 2 in order to have 2 electrons. Therefore, writing the overall equation, so far we would have Fe2+ and 2 of them, plus H2O2 plus 2H plus 2 electrons goes to 2 Fe3+ plus 2 electrons plus 2 H2O. Next we can cancel out. We will cancel out first our electrons, and that's all we can cancel out in this equation. So that makes our overall equation 2 Fe2+ plus H2O2 plus 2H+ goes to 2 Fe3+ plus 2 H2O. To get the mark for this question, you need to have the correct overall equation for the oxidation of Fe2+ by acidified H2O2. Part 2. Zinc reacts with acidified Cr2O7 2- ions to form Cr2+ ions in 2 stages. Explain why this happens in terms of electrode potentials and equilibria. Include overall equations for the reactions which occur. In the first stage of this reaction, we're going to react zinc with acidified Cr2O7 2-. Here I've highlighted the 2 electrode potential equations we're going to be using in this question. Firstly, we need to identify the more negative electrode potential because its equilibrium will shift backwards, and then the more positive electrode potential, its equilibrium will shift forwards. So if we begin by writing the equations, we have zinc goes to zinc 2+ plus 2 electrons, and then chromium 2O7 2- plus 14H plus 6 electrons go to 2 chromium 3+ plus 7 H2O. So we can create an overall equation for this stage by scaling our electrons. So that means we need to multiply the zinc equation by 3 in order to create 6 electrons. So writing the overall equation, we would have 3Zn plus Cr2O7 2- plus 14H plus 6 electrons goes to 3Zn2 plus 6 electrons plus 2 Cr3 plus 7 H2O. We can then cancel out the electrons from both sides of the equation, which makes our overall equation for stage 1 3Zn plus Cr2O7 2- plus 14H goes to 3Zn2 plus 2Cr3 plus 7 H2O. In the next stage, we're going to react zinc with chromium 3+ and use this electrode potential which I have just highlighted. Like for stage 1, we need to identify the most positive and most negative electrode potentials. The most positive is the chromium electrode potential, so it will shift forwards, and the zinc is still the most negative, so it's going to shift backwards. So rewriting these two equations, we would have Zn goes to Zn2 plus 2 electrons, and Cr3 plus an electron goes to Cr2 . Next, we need to scale the electrons, so that means multiplying the Cr equation, or chromium, by 2. So then we have 2 electrons in both equations. So that means our overall equation would be Zn plus 2Cr3 plus 2 electrons goes to Zn2 plus 2 electrons plus 2 Cr2 . Next, we can cancel out the 2 electrons on both sides of the equation. That would then make our overall equation Zn plus 2Cr3 goes to Zn2 plus 2 Cr2 . So we have completed both stages of this question, and zinc has reacted with acidified Cr072- to form Cr2 ions. Then we need to explain why this happens in terms of electrode potentials and equilibria, which is what the question's next asking us to do. In our explanation, we need to make a comment on the electrode potential of zinc and the fact that it is more negative. Then you need to compare, because it's more negative than the electrode potential of Cr2O72-. So we're commenting on the first stage of this question. And what this means is that the zinc system shifts left. We've shown this in our working because we've said it shifts backwards, but saying that it shifts left is a bit more specific. To get the 4 marks for this question, you get a mark for each correct overall equation. You get a 3rd mark for commenting on the fact that the electrode potential of zinc is more negative than the electrode potential of Cr2O72-, and your 4th mark is commenting on the fact that the zinc system shifts left. Part D. 3 different reactions of copper compounds are described below. Reaction 1. Aqueous copper 2 sulfate reacts with an excess aqueous ammonia in a ligand substitution reaction. A deep blue solution is formed containing an octahedral complex ion C, which is a trans isomer. Reaction 2. Copper 1 oxide reacts with hot dilute sulfuric acid in a disproportionation reaction. A blue solution D and a brown solid E are formed. Reaction 3. Copper 2 oxide reacts with warm dilute nitric acid in a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating basin. A hydrated salt F crystallizes with the percentage composition by mass Cu 26.29%, H 2.48%, N 11.59%, O 59.63%. Identify C to F by formulae or structures as appropriate. Include equations and any changes in oxidation number and working. If we first highlight the key pieces of information in reaction 1, we're reacting aqueous copper 2 sulfate with an excess of aqueous ammonia in a ligand substitution reaction to form complex ion C. That means that the reactants for this equation would be CuH2O6 because we're using aqueous copper 2 sulfate, and then 2 plus because of the 2 in brackets, plus 4NH3, which is ammonia, and then we would produce complex ion C, which would be CuH2O2, NH3, 4, square brackets 2 plus because our charge hasn't changed. And then to balance the equation, we need to have 4H2O. So if we rewrite C, that is Cu, H2O, 2, NH3, 4, square brackets 2 plus. I've rewritten it just for the clarity for the marker so that they fully understand that you know what you're talking about. Next, we're asked to show the octahedral complex ion, or the structure. So we're going to use a 3D diagram, which means we're going to use wedges. Firstly, drawing out an octahedral layout with wedges. This is something you need to know because it's a standard thing that comes up when talking about transition metals in particular, which is what this question's asking. So here I've drawn our octahedral layout with wedges, and then we need to add our H2O and NH3s onto this layout. So our H2Os would go at the top and bottom, making sure that the copper bonds to the oxygen in the H2O, and then the ammonias or NH3s will go around and the copper will bond to the nitrogen. So making sure that this is clear all around the molecule. So N3H is what I've done on the left, just to show that the copper is bonding to the nitrogen. And then we're going to have square brackets with a 2+ charge because it's an ion. C is an ion. The reason that I've put H2O at the top and bottom, or on opposite sides of this complex ion, is because we're told that it's a trans isomer. Looking at reaction 2, we have copper 1 oxide reacting with hot dilute sulfuric acid in a disproportionation reaction. A disproportionation reaction means that oxidation and reduction happen simultaneously to the same element. So we need to find D and E in reaction 2. So firstly, writing reaction 2, we would have Cu2O plus H2SO4, which is copper 1 oxide reacting with dilute sulfuric acid. And then that would produce CuSO4 plus H2O plus Cu, or copper. So identifying D and E, D would be CuSO4 because we're told that D is a blue solution and copper sulfate is a blue solution. And then E would be copper on its own because it's a brown solid, and we're told that E is a brown solid. Next, we need to show that this reaction is a disproportionation reaction. We do this using oxidation numbers. So we need to first calculate the oxidation number of copper in Cu2O. So we know that oxygen has a 2- oxidation number, and so Cu2 must have a 2+ oxidation number. So dividing that by 2 to get Cu on its own, or copper on its own, is 1+. Then copper sulfate, that would have a 2+ charge, and that is because a sulfate ion has a 2- charge, and any compound must have an overall oxidation value of 0. Copper on its own, therefore, would have an oxidation number of 0. So we can write that copper goes from +1 to 2+ and 0 in terms of oxidation numbers. Then looking at reaction 3, we have copper 2 oxide reacting with warm dilute nitric acid in a neutralization reaction to form a blue solution. So firstly, writing this reaction, we would have CuO plus 2HNO3 because that's nitric acid, and that would produce CuNO3 brackets 2 plus H2O to balance the equation. Next, we're told that the unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating basin, and the hydrated salt F crystallizes with the percentage compositions by mass, which we're given. That means we need to work out the empirical formula of the hydrated salt F and the molecular formula, but first, empirical formula. That means we take the percentage, so for copper, that would be 26.29 divided by 63.5. For hydrogen, that is 2.48 divided by 1. For nitrogen, that is 11.59 divided by 14. And for oxygen, 59.63 divided by 16. So that would give us for copper 0.41, for hydrogen 2.48, for nitrogen that gives us 0.82, and for oxygen that gives us 3.72. So then we divide by the smallest, that would be 0.41, to get our empirical formula, and then we can scale up for our molecular formula. If we're left with a 0.5, for example, we would scale up by multiplying by 2. But if that's not relevant, then that would be our molecular formula we're going to produce. So dividing by 0.41, we get 1, and then we get for hydrogen 6, for nitrogen 2, and oxygen we get 9. So that makes our molecular formula CuH6N2O9, and it's a hydrated salt, so we're going to have FbCuNO3, 2, because that's what's produced in equation 3, and then the hydrated would mean a 0.3 H2O for F, or hydrated salt F. To get the 6 marks for this question, you need to have all 3 reactions covered in detail with C, D, E and F identified with clear explanations and equations with oxidation numbers and structures being correct where appropriate.